Okay, we're back and we're solving systems of equations by graphing. So we can make a table of values for the first equation here. I just need to think of two numbers that add up to be 6. You could use the intercepts, or you could just think of any two numbers, 0 and 6, 3 and 3, 2 and 4. Those are some ordered pairs. Each of those adds up to 6. So 0, 6, 1, 2, 3, 4, 5, 6. I know you can't see me counting, which is unfortunate. 3, 3. It's right there. And 2, 4. So there are 3 points. We'll draw the line. And that's equation 1. That's what it looks like. Equation 2. We can do the same thing. We can make a table of values. This time I have to think of two numbers that if I take x minus y, it'll equal 2. So maybe I want to say 4, 2. That would work. 5, 3. That would work. Let's put in 0. If we put in 0 for x, we would get -2 for y. You can think about that one. You could write those equations out, but I'm going to graph these ordered pairs. 4, 2, right there. 5, 3, there. And 0, -2, which is right there. All right, that line's going this way. So what's the point of intersection? Let's try the yellow highlighter this time. I think the point of intersection is like right there. And it looks like that is about the point 24. Now, if I plug in those numbers, would I get that? Well, 2, 4 works for equation 1. And 2 minus 4 is not 2, so that one doesn't work. In fact, it's off a bit. Oh, because the point is 4, 2. Okay. 4, 2. And that does work. So you can try those. You can write them out like we did for the very first problem. Write out to see whether it's a solution or not. But remember, sometimes your graphs are going to be off a little bit. All right, we'll go to a second page then. We have a few more to do, some different lines. Here we have our first line, which is just y equals -1. So I don't know if you remember, there's no x though. That makes a horizontal line at -1. Oops, at -1. Let me erase that. So that line's going to be down here. Kind of an advantage on that. We know y is -1. But let's graph the other line then, the second line. So maybe we don't want to do a table of values this time. We could say 3y equals -x plus 6. Then we could divide each term by 3. And we would get y equals -1/3 x. That's going to be our slope, -1/3, plus 2. And so we have a slope of -1/3 and an intercept, a y-intercept of 0, 2. So we'll graph the intercept, 0, 2, right there. And now we're going to use our slope to count the rise and the run. So we're going to go down 1 and to the right 3, down 1 and to the right 3, down 1 and to the right 3. And so there's our line. And do we see where they intersect? I'll go back to my green pen. Looks like it intersects right there. And that's the point, it looks like 9, -1. Now we knew that y was going to be -1 because it told us that in the first equation. If you try them in both equations, they work. All right, so let's go to the next one. We've got our first line. It's already in slope-intercept form, so the y-intercept is 2. The slope is negative 1/4, so down 1 and over to the right 4, down 1 and over to the right 4. That's enough. We'll try to draw a line. All right, now let's look at the other equation. We don't have it in slope-intercept form, so we could put the x, oh my gosh, I don't know where it did that. Get it back here. 4y equals negative x minus 8. So if I just move the x to the other side, I can get that. If I divide each term by 4, you could also do a table of values here, but you're going to get y equals negative 1/4 x minus 2. Okay, so our intercept's at negative 2, and our slope is down 1 and to the right 4. Down 1 and to the right 4. We get another line. And those two lines are parallel. So they don't intersect, they don't cross. It's like railroad tracks. These are parallel lines. Parallel lines have the same slope, okay, because the slopes are equal. So if that happens and you're graphing two equations and you find out the slopes are the same, they're not going to intersect. Well, what does it mean for the solution? It means there's no solution. And we'll just write out no solution. So that's a special case. It happens. Sometimes the lines don't intersect, and that means they're parallel lines. Okay. Put the 2 there so nobody knows. All right, we've got one more. I think one more. All right, the first one is in slope-intercept form. So we'll call this line 1. It's got an intercept of negative 6 and a slope of negative 3 or negative 3 over 1. So I can count down 3 and over 1. I'm kind of out of room, so I'll go up 3 and back 1. That will work as well. And I get that line. Now my other line is not in slope-intercept form, but let's see if we can put it in slope-intercept form. So 2y equals negative 6x minus 12. So divide both sides by 2, so dividing each term by 2, and I get y equals negative 3x minus 6. Now, you may notice that that looks exactly like the first line we graphed right there. But let's say you didn't notice that and you're like, okay, I'm going to graph my slopes at my intercepts at negative 6. I'm going to count my slope. And I get a point there and a point there because the slope's the same. And you see that it's actually just the same line. Well, what does that mean? It means they didn't give us two different lines. They gave us the same line. It's just one looked a little different. What does it mean for the solution? It means there are infinitely many solutions. All the solutions are on that line that we have drawn, but all the points on that line are solutions to the system. So we're just going to say there are infinitely many solutions, and we'll go on. Oh, I'm not seeing the last page. Well, I remember what it talks about. So we have some terminology. Sometimes we have solutions that are intersecting lines. Intersecting lines. I guess I should say systems. intersecting lines are going to have one solution. That point of intersection is going to be the solution. Sometimes we have parallel lines. Parallel lines, they aren't going to intersect. That means there are no points that will satisfy both equations, and so there's no solution. And sometimes we have coincident lines. It's not spelled very well, but coincident lines, they're really just the same line. So there's an infinite number of solutions. Yeah, I think they say infinitely many solutions. And then they're going to talk about the terms independent and dependent and inconsistent and consistent. Let's see what we have here. When we just have one solution, so for intersecting lines, they are independent and they are consistent. You can find a solution, and so they're kind of the best of both worlds. Parallel lines, oh, that's not how you spell parallel. Parallel lines, they are independent, but they're also inconsistent. And then finally, the coincident lines, try to spell it right this time. They are dependent, but they are consistent. Okay, so let me do one thing real quick just to check something here. See if I left anything out. No, I think we got it all. Okay, so those are your notes, and we will see you in class.